history of planetary motion with Dave Chapman on episode 475 of the Actual Astronomy Podcast. I'm Chris, and joining me is Shane. We are amateur astronomers who love looking up at the night sky, and this podcast is for everybody who enjoys going out under the stars. So today we are welcoming back Dave Chapman, who has been a guest several times on our podcast, and in particular, he curated the Stars You Should Know series for us, which I think these were just about our most popular episodes, weren't they, Shane?
Yeah. There was a lot of listens to those ones, and I think those ones maybe generated, probably the largest amount of email feedback too, of just people telling us how much they enjoyed those episodes as well.
Yeah, and out of all the episodes that we've done, that's the series that I actually refer back to when I'm doing my own observing, because one of the central tenets to those podcasts were that many of those stars are the guide stars that are in the databases when you're aligning your equipment. Some of them, I just wasn't familiar that much familiar with. So by having those podcasts kind of in the back of my mind, as I'm doing that, it actually helps with doing the alignment of your mounts and other instruments. It's pretty cool. All right. So if you want to know more about Dave and his content, you can go and check those out. But without further ado, since we have a lot to go over here, essentially, Dave, you're going to review the history of our understanding of planetary motion from prehistoric times and antiquity to the present day. So, Dave, that seems like a very light topic we should be able to cover in 30 or 40 seconds. Welcome,
Yeah.
welcome back. Welcome back, Dave.
Thank you so much for having me back. Yeah, it's a lot to cover. I just wanted to say that, yeah, I enjoyed doing the previous podcasts I've done with you, and I'm pleased to hear that the response was favorable. So this one is kind of special. The full title is "The Wanderers: A History of Planetary Motion," and it is the oral version of an essay that I wrote back in December that I submitted to the Griffith Observatory Annual Science Writing Award. So this is an award where they invite people to write articles, and there's prizes actually. And then the winners also get published in the magazine. So the Griffith Observatory, of course, is that observatory in Hollywood, Los Angeles, California. And it's actually a locale for very many films, but that's another story. I myself and Kathy LeBlanc, we wrote an essay on our Mi'kmaq Moons project and submitted that in 2016, I think, and we won second prize. So that's why I know about it. And every year they send me a reminder that the deadline's coming up. I've always wanted to do this topic, and I made myself do it. It was hard work in December. It took a lot of reading, and it took a lot more work than I really had bargained for to try to distill it all down into sort of common language that the average educated person would, be able to follow without having any background in astronomy. So this is, I've sent it in. I'm waiting to hear back. And really, this is the first time that anyone else has really been able to experience the ideas in it. So let's just get going.
All right, Dave. So what is this about exactly? Just want to do a bit of an introduction here for us?
Yeah, well, I'll do that. So it's the story of how humankind became aware of the planets in the solar system and learned over the hundreds and hundreds of years how they move into the sky and how they could predict them. And then in the end, you have an app in your pocket, in your mobile telephone that can tell you where the planets are at any instant. Asteroids. How is that even possible that today we can do that with our phones? So that's basically where I'm headed. And it's got an interesting twist, I think, story when we get to the end. So what I'm looking at here, I'm going to be talking about the 5 classical planets that were apparent to the ancients, Mercury, Venus, Mars, Jupiter, and Saturn. of course, Earth, but in those days, Earth was Earth was Earth and everything else was a planet. Now we know it's a planet too. I'm also going to have a little discussion about two planets that were discovered using telescopes, Uranus and Neptune, and we're going to spend a little bit of time talking about the smaller body Ceres, which is now a dwarf planet. Now, all of what I'm talking about here applies to everything. I'm not going to get into what is a planet, like those kind of discussions. We're not going there. Planet, minor planet, dwarf planet, it's all the same. So we're going to focus on the motion of these solar system bodies and how, over time we be better, not only at recording their positions in the sky, but also predicting those positions using mathematical and computational tools. So today, we understand the motion of the planet so well that we can build a spacecraft on Earth, launch them into space, and send them to any solar system body we choose. We can even have them come back with samples from certain bodies. I mean, that's how far we've come to be able to send things off and bring them back and so on. And none of these achievements would be possible without the knowledge of celestial mechanics and planetary motion that developed over these couple thousands of years. So I'm going to start with prehistory and antiquity. So imagine our earliest ancestors, Stone Age hunters and gatherers. They must have gone out and looked up at the sky and seen things in the sky. Who knows what they thought of them? Who knows what they imagined? Did they even notice planets being different from stars? We don't know. We've seen carvings in drawings in caves, and lots of people speculate about what those things are all about, but we don't know. It's all speculation. We can only imagine. When agriculture developed, people settled down and gathered in cities, and I guess they lived in a different way. The cave pictures became alphabets. They developed written language, not written language that we could easily read today, but we figured it out. And so they started writing down all kinds of things. They started talking about battles and kings and queens and floods, but they also started writing down observations of things in the sky, the sun, the moon, and planets, particularly Venus. Venus, was being the brightest planet, was of great interest to the ancients, and they would write down its appearances and they would record it, and they use kind of arithmetic to try to keep track of the patterns and to predict, when it would be visible again. Just wondering if either of you, are you familiar with the 8-year cycle of Venus, the Venus apparitions?
Lately, Dave.
Okay.
I haven't studied it very much myself.
Yeah, doesn't it form like a sort of a pentagram type shape if you were to draw out all the
Yes.
elongations and that sort of thing?
It's not a precise resonance, but it's a pretty close resonance, pretty close to a resonance. So you're right. The pentagram comes from, 5 synodic periods of Venus turn out to be 8 years on Earth and 13 Venusian years. So they're sort of round numbers. So what happens is every 8 years, the pattern of Venus, where Venus goes in the sky, repeats almost exactly. So like 8 years ago, like Venus now has been very high during the winter, and it's approaching inferior conjunction quite quickly. 8 years ago, it did the same thing. And I just realized that 40 years ago, which is 5 cycles of 8, 40 years ago, it did the same thing. And back then, I was observing it. And I actually was able to observe Venus in the evening sky and the morning sky around conjunction. And I wrote an essay, and that's what won me the Simon Newcomb Award. That's where I became aware of all this. And that was 40 years ago. Anyhow, so I've been very interested in that. Anyway, the ancients were aware of this. And so the Mesopotamians and the Babylonians Is that the same thing? I'm not. I'm not much of an. I'm not much of an ancient history buff, but the Maya across the ocean, they were also making records of Venus. So so these early sky watchers, they recognize patterns of stars that remain fixed in position, and they know they started seeing patterns and constellations, but they also started noticing that some of these stars were moving around. They didn't stay in one spot. And the ancient Greek word for those stars that didn't remain fixed position was planetes, which is today we have the English word planets. So these were the wandering stars, and that's why I call my essay, the essay's called "The Wanderers." This is all about the wandering stars or the planets. Now they didn't know what they were, but they just saw that they moved differently, and they connected them with mythological beings or gods, spirits. You know how it goes. They made up stories about them. So the all of the classic planets were connected with Greek gods by the same name. Mercury, Venus, Mars, Jupiter. Well, those are the Latin names. There were Greek names, equivalent Greek names as well. And so the Babylonians, they recorded their observations in tables of numbers, and they didn't really graph or plot the positions of the planets, but they noticed these zigzag motions. And when I mean zigzag motions, there's these retrograde motions that are very important, particularly Mars, Jupiter, and Saturn. And I have to explain that. So normally, the stars from day to day go from, if you look at them at the same time of night, they go from east to west in the sky through the seasons. The planets, if you look at the planets relative to the stars, they go the opposite way. They're marching through the stars from west to east, typically. But every so often, like Mars, Jupiter, or Saturn, they stop, and they turn back, and they go backwards towards the west again. And that's called retrograde motion. And then they get in the middle of that, they have these oppositions, or they're totally opposite the sun. Then they come to another stationary point, and they turn around again and continue their eastward progression until the next time there's a retrograde loop. So the Babylonians actually recorded these as sort of zigzag patterns. So I mentioned oppositions during retrograde motion. That's when they're opposite the sun. That's when they're the brightest. That's when they move the quickest. The other important key position is conjunctions with the sun, which are they're mostly unobservable. So they were aware of these motions and recorded them and tried to predict them. But they didn't really have like any model of what was going on or any kind of concept of the cosmos. I don't feel like they just saw these things and recorded them, and we have those records to go back to. There's quite a few books on this kind of thing. So it wasn't until the Greeks came along. The Greeks were master mathematicians. I don't know where it all came from, but the Greeks, they invented geometry or they acquired it from somewhere, or they developed geometry and math. All those guys, Euclid and all those guys. They were really fascinated with circles and spheres. They thought them to be very pure geometrical figures. So they figured that somehow the motions of the planets must have something to do with some sort of geometry. And so they were the first to really apply any kind of geometry or model to the heavens. So
you asked the question, so I'm going to answer it.
Okay.
Where did it come? And this is a whole different type of podcast, but
yeah,
originally the Egyptians created some mathematical-ish models, and it was Plato and some of the other philosophers who went and started to look at that in a more objective
Right.
of way
Yeah.
that eventually led into this. So this is a progression of really
Yes.
started as more of a I guess in a way like a theological type of situation to a philosophical one to
Yeah. Natural philosophy, right?
natural
Yeah.
philosophy to a practical science. Yeah.
They went away from the heebie-jeebie and they were trying to find some. Well, Aristarchus, who I don't know much about, other than he's got a crater of the moon named it. He actually he actually came up with the idea that everything was going around the sun. He was the first person to come up with that. It didn't catch on right away, but somebody came back to it. The other thinkers, they thought that things basically went around the Earth. So the sun and the moon went around the Earth. I mean, that seems pretty, that's pretty easy to accept. I mean, it's not too far. I mean, the moon does go around the Earth, and the sun apparently goes around the Earth, but that's just a matter of perspective. But the other planets, they had them going around the Earth too, but it didn't really explain, the retrograde motions and oppositions and all of that. So a fellow named Apollonius, actually, he was around 240 to 190 before the Common Era. He came up with the idea of combining circular motions, and this is very important. So he had these big circles. He had a big circle for a planet. It was called the deferent, and then there was a small circle called the epicycle. All right, so there was a big circle and a small circle, a circle upon a circle. And so the way he imagined it was the center of the epicycle, that is the small circle, would uniformly move around the circumference of the deferent, the big circle. And the planet itself revolves around the circumference of the epicycle. So there's these two circular motions imposed on one another. And if you adjusted, the sizes of the rates of these things, you could reproduce in a rough way the stationary points and the retrograde motion of the planets. So, the backwards motion, the two stationary, and the variable brightness. So it was actually a pretty successful idea. Unfortunately, they try to fit those things to the observations. Well, the observations weren't all that accurate. So what happened here is there was this leapfrog thing that happened where, um, as the models progressed, they realized that it wasn't predicting the positions of the planets, and then as the observations progressed, they realized that the models weren't working. So what happened was they said, well, we need more of these epicycles to make it fit. So they'd have a circle upon a circle upon a circle. Okay. And so they kept on adding epicycles, and it ended up with, like, we call it the Ptolemaic system. Claudius Ptolemy, he was 100 Common Era to 170. That's when he lived. But he had like 40 epicycles at the end of this. I mean, it was getting ridiculous. Like, how could this be? There was no simplicity to this. It was just very complicated. And so anyway, but even Ptolemy himself, I don't know if he believed that this was like physically true, like this was actually what was going on. He himself said, well, really, it's just a way to predict where they're going to be. Like, so he didn't really read too much into it in terms of cosmology. Anyway, that model endured for many centuries, and it's a geocentric model. Everything's going around the Earth, and then there's these epicycles. Very little advancement was made over the next 10 centuries or so. This information got passed around. I think the Persian and Arabic astronomers picked it up and kept it going, but nobody really added to anything. I don't know if that includes the Dark Ages, when things were not going well in Europe. But I'm not really a historian, so I'd have to check that. So the next big revolution in the view of the planetary motions was Copernicus. Now Copernicus lived from about 14 well he lived from 1473 to 1543, so relatively modern, 400 years ago, 500 years ago. He was Polish by birth, but he moved to Italy. I think he might have been anyway, he was educated in Italy. I don't know if he was a priest or not. He might have been in the church. And he studied, so he sort of revived this idea of Aristarchus, of the heliocentric model. I don't know exactly what inspired him to do that, but he was looking at the heliocentric model, and he figured out that if you had everything going around the sun in circles, that all of these epicycles, well, for the large part, the many epicycles were not needed. So he came up with this vastly simplified mental model of what the planets were doing. It explained why Venus and Mercury didn't go far from the sun. It explained the retrograde motion of Mars, Jupiter, and Saturn without, easily enough. The only hitch was he liked to use perfect circles as well, and which is natural, but he just sort of rearranged how things went. But he had to include little epicycles in his heliocentric model to maintain accuracy. So that was kind of like, yeah, in order to get rid of that last epicycle, something else had to happen. He didn't publish his views because they were contrary to the teachings of the church. I think he basically published his book on his deathbed, and so it took a long time for this view of heliocentric cosmology to catch on. Again, the church was in it. So the person who's really gets the credit for putting the death knell to the geocentric model is Galileo. Now, Galileo did a lot of stuff. He lived. I don't think he overlapped with Copernicus. He was aware of Copernicus's teachings. He lived from 1564 to 1642, but he did a lot of very interesting things, as we know. But for astronomers, the most important thing he did was in 1609, he pointed a telescope at the heavens. Now, he didn't invent the telescope. It had already been invented by the Dutch, but he heard about it and decided he wanted to make one, initially for other uses. But it was his idea to turn it on the heavens, and that was where things really started to happen. And he shared his observations. So he did two things that kind of make him amongst the first scientists, if you think about it. He observed, he observed and collected data, and he shared his observations. So, to be a true scientist, you have to do both. You have to observe and you have to share. So other people can appreciate what you've done and maybe build on it. And there's two significant discoveries that he made that support heliocentric cosmology. One was observing the planet Jupiter. He saw a disk, and he saw four smaller bodies revolving around Jupiter. And so that didn't prove anything, except for the first time with his telescope, he could show that not all bodies in the universe go around the sun. You see? He found some things that were revolving around another body. And so that was very significant discovery. So the idea that everything goes around the sun because the sun's the most important thing and the center of the universe, that kind of went out the window. The other thing that he observed with his telescope in relation to this topic was that the planet Venus showed phases that changed with time, much like the moon. And that would be completely in line with the heliocentric model, with Venus going around the sun and Earth going around the sun. That completely you would expect phases of Venus. So those are the two major things that he introduced. And he also started studying mechanics and stuff like that, um, momentum and the motion of things, dynamics. And he really paved the way for Newton, uh, Newton's laws of motion. So, did you have any thoughts about Galileo and his contributions?
Shane?
Nope.
I don't know that I have a lot to add to that.
Shane has Galileo right behind him, so that's why I
Yeah.
was.
Yeah, I guess the wood carving.
Okay.
Yeah.
Well, maybe we'll just move on. So the next two guys are Tycho Brahe and Johann Kepler, who overlapped a little. Um, Brahe actually was born a little bit before Galileo, and Kepler came later. Um, so there was a bit of overlap between Galileo and Kepler. So Tycho Brahe was a Danish astronomer, and I would say he was the greatest astronomer of the pre-telescope age. He didn't have telescope, but he had lots of instruments for measuring angles and positions, and he made multiple accurate observations of the stars and planets. And he had this observatory in Uraniborg that was financed by his patron King Frederick II. So he got a stipend to do this work. He had some idea of a cosmology. It was kind of halfway between Ptolemy and Copernicus. Of course, he wouldn't. I don't think he knew anything about Copernicus. No, he would have. He would have, but he didn't go whole hog after the heliocentric. But he had the planets revolving around the sun, but then he had the sun and the moon revolving around the Earth. Well, no complaint there. The moon goes around the Earth, but he had the sun going around the Earth. But that's not much different from the way it is, because it's just a matter of perspective. I mean, you could say everything's going on the sun's going on around the Earth. From our perspective, that's what it looks like, but it's the same as the Earth going around the sun, right?
Mm.
So it's really a matter of viewpoint. But I guess he just couldn't be that the Earth was the center of things. Now, what happened was Frederick II was succeeded by Christian the Fourth, who for some reason did not like Brahe, and he got his stipend cut off. So he wasn't supported by the Danish court. And he went off and found a new patron, Emperor Rudolf II of Germany. And he relocated to the city of Prague, which is now in Czechia. Have you guys, either of you, been to Prague?
Never been.
Not me. No.
Well, it's really a cool place, and there's actually a really cool, fairly large statue of Brahe and Kepler that I stumbled across. I didn't even know it existed. I was just walking around the city, and I came across the statue. Who are these guys? This is Tycho Brahe and Johann Kepler, and there's all kinds of little hints and memories. There's a Kepler lane, and this kind of thing. There's quite a lot of references to them in the city. It's a beautiful city. It's kind of the bridge between the East and the West of Europe that's really worth going to. And it's, at least when I went, it was a cheap holiday. The beer was not expensive, and they have jazz clubs and coffee houses. I mean, it's a really, really lovely city. Somehow it escaped being trashed during the war, which is a good thing. Anyhow, so Tycho Brahe had oodles and oodles of accurate positions of the planets. And he wasn't. Yeah, he never heard about Galileo's telescopic observations. He died in 1601, so he wouldn't have known about Galileo's work. But his German assistant, Johann Kepler, was relatively young, and he continued Brahe's work. he was much more mathematical. So he delved into all this data, and he was aware of Galileo's work. He was aware of Copernicus. And what he did, his contribution was he took these precise observations of Brahe, and he started studying, the detailed motions of the planets. And so what he ended up working out was that there were no perfect circles, epicycles. He worked out that the planets moved on ellipses. Okay. And he did this by purely from looking at the data and kind of inferring like what sort of conic sections. He realized right away. Well, not right away. After he did all the work, after he did all the reconstruction, he realized that the positions of the planets. He started with Mars and the Earth, and worked out that they were on elliptical orbits. Not highly elliptical. Mars more so than Earth, but he realized that the planets had to be elliptical. The orbits had to be elliptical. And he also, so that was his first law. And he also, so anyway, he also worked out his equation, Kepler's equation, which worked out how fast these planets moved along these ellipses. So his second law was, it was a little bit abstract, but he stated it this way. He said, a line connecting the planet and the sun will sweep out areas equal time as the planet moves around its orbit, which sounds kind of abstract, but it accounts for the varying orbital speeds of the planets. And we now know today that this is actually what's called the conservation of angular momentum. So if you have any central force motion, any motion where the acceleration is caused by an attraction to a central point, will give you this law, this second law, the conservation of angular momentum. Doesn't have to be an inverse square law. It could be any kind of central motion. It could be a ball on a string. Okay? So you have this conservation of angular momentum. He didn't understand it, but that he saw that. And he developed the so-called Kepler equation, which worked out where the planet would be, along the ellipse. And it's a difficult equation to solve. You can't just write down the answer. You have to solve it numerically. Later on, he published his third law, which relates the period of the planet's orbit to the major axis of its ellipse. Not so important for what we're talking about today, but those are the three Kepler's laws. So the point is that he discovered the how of the planetary motion, but he didn't know why. He didn't know what made the planets move in the way that they did. I don't know what he imagined, that something was pushing them along, or anyway, he didn't know. He figured out the how, not the why. Anyway, no more epicycles, not necessary. That was his those big contributions to celestial mechanics. So to figure out the why, we have to come to Newton and Halley. And Newton developed his three laws of motion that dictate how objects move and interact. So one of them, he has his three laws of motion, which I won't go into. Most people are aware of them. But he sort of took Galileo's ideas and codified them. And eventually he published these in a book called, they call it the Principia these days. But the other thing he did, thinking about gravity, it came to him when things fall to Earth. The legend has it, he saw an apple fall to Earth. I think that's a legend. But he appreciated, he said, if there's something pulling things together, gravity, he thought that this should be common in the entire universe. That's why he called it the universal law of gravitation.
I think the full story is that he spent a long time sitting under a tree at his parents' house during a pandemic
Yes,
when
that's true.
when everybody was isolated. So it's sort of boiling down a truth
Yeah,
into a soundbite.
yeah. There's actually an article in Rask Journal somewhere where somebody poo-poos the whole Apple story and the falling on the head for sure. Anyway, he came up with this idea that this universal gravitation should be the inverse square law. And he worked out that if you combine this inverse square law of gravitation with his three laws of motion, that you get elliptical orbits, the Kepler's elliptical orbits. So he discovered the why. Now, the problem is he did it, but he didn't, I don't know where his head was. He did this when he was a young man, but he didn't bother writing it up or telling anyone about it. He just said, okay, that's cool. So Edmund Halley, who was an astronomer, came to see him. He said, look, we're trying to figure out what's going on with these comets. Do you have any ideas? And Newton said, yeah, it's gravitation, laws of motion, uh, elliptical, Kepler's ellipses. And Halley was astonished that he had it all figured out, but hadn't really communicated any of this information. So Halley actually paid for and managed the publication of the Principia on behalf of Newton. This was 20 years after he had done all the work, okay? Moreover, Halley learned about these methods and he started applying them to comets and trying to understand the motion of comets. And he discovered that there were great comets from the year 1456, 1531, 1607, and 1682. And he worked out the orbits of them using Newton's methods.
Wait,
and he
was that the same comet?
Eh?
Was that the same comet?
Yes, it was. He found out that these comets essentially had identical orbits and were coming back whatever the period is, 76 years.
Yeah.
And so that was his big discovery. And he predicted it to come back in 1758, but he didn't live to see it. And how sad. So anyway, that's why it's called Halley's Comet, because he figured out the motion. And so in the modern configuration, we call that comet 1P/Halley. P for periodic, 1 for the first one. I think there's only, I don't even know if there's as many as 200 periodic comets. No, most comets are not periodic. They're in hyperbolic orbits, come once, go back, and never come back. So anyway, amazing, eh? So then the world knew about these, how to do this. And the next big advancement came from the largely French mathematicians. So it turns out that Newton's ideas only work for what's called the two-body problem. You have two bodies revolving around one another. One of them might be more massive than the other. You get perfect elliptical orbits. It's a well-known solid answer. If you put even one more body into that system, it disrupts this elliptical harmony because all of the forces, the accelerations from the third body start messing around with the first two. That problem is called the three-body problem. And it's basically, you have to solve it numerically. There's no, you basically have to work out all the forces and the tugs and just kind of integrate it. There's something called the restricted three-body problem where the third body has like vanishingly small mass. And so where it doesn't affect the first two, but then the orbit of the third body gets really wacky, So luckily, in the case of the solar system, we have the sun is very dominant. So for the most part, all of the planets look to be going around the sun in elliptical orbits. But it turns out that when they push and pull on each other, those orbits get changed. They slowly change in time. And these little pushes and pulls are called perturbations. And the people who worked out the mathematics of this, one of them was Joseph Louis Lagrange, and the other one was Pierre-Simon Marquis de Laplace. So there's Lagrange and Laplace. Lots to say about them, but I don't have time. So what they did was they would initially solve for the elliptical planetary orbits around the sun, and they developed, so then these orbits would have orbital elements, numbers that define the size, shape, orientation of the orbit, plus the original position. There's two numbers for the orientation. So 1, 2, 3, 4, 5. I'm missing one here. Anyhow, there's 6, I believe. So they developed the equations to figure out how the tugs of the planets on each other would change those orbital elements over time. So when you look in the RESC handbook, you see these tables. They're called osculating orbital elements. They're only good for the time that they're displayed, and they change from year to year. So a little after that, William Herschel discovered the planet Uranus in his telescope. It created quite a stir because all of a sudden the planets went from 5 to 6. So we have this new planet, and it turned out that it occupied a nearly circular orbit well beyond that of Saturn. And they were able to, study the orbit of that. We'll come back to Uranus later. The other individual at this time who contributed a lot was German mathematician Carl Friedrich Gauss. And he developed the method of least squares to find the best fit of an orbit to the observations. And he figured out that you could, with a minimum of 3 observations, you could work out the orbit. It's better if you have more, but with 3 observations, you could work out the orbit and predict where it was and where it was going to. So one of the successes of his technique was when Giuseppe Piazzi discovered the first asteroid. Well, he discovered this new planet Ceres on the 1st of January, 1801. Well, they called it a planet, but then they discovered a whole bunch more in the same part of the solar system. So then they started calling them asteroids. And then in 2006, Ceres is now a dwarf planet. So it's been a planet, a dwarf, an asteroid, and a dwarf planet. Anyway, Piazzi was observing it, but then he had a lot of great observations. He didn't communicate his observations right away. It moved into the sunlight and couldn't follow it, so he lost it. But Gauss, based on Piazzi's observations, calculated where it would be found, and after it came out from behind the sun, they were able to predict its position and find it again and continue following it. So he sort of developed that technique. And they discovered that the orbit of Ceres was between Mars and Jupiter. Now there's like 1 million additional minor planets in that area, and most of them unnamed. So I'm going to get back to Uranus. Later that century, the 1800s, a Frenchman, Urbain Le Verrier, he was interested in looking at the orbits of Mercury and Uranus. Sorry, Mercury and Uranus. And first of all, he looked at the orbital precession of the perihelion of Mercury. So Mercury's orbit the whole orbit was rotating around the sun, and the perihelion was moving. And they could not explain that by taking into account all the perturbations from all the known planets. Le Verrier thought there must be another planet out there. So he was looking for this planet Vulcan. Well, they never found the planet Vulcan. And so the precession of the perihelion of Mercury remained like a total mystery. Then he said, okay, I'm going to go look at Uranus now, because Uranus, even though they had the orbit figured out, it had oddities. And he said, oh, there must be another planet out there. Now, this time, he was able to calculate where such a planet might lie and how large it would need to be in order to explain the oddities of the orbit of Uranus. This is like doing perturbation theory in reverse. It's like you have to pretend. You say, "Oh, well, I think it's here," and we think it's this big. So what happens to the orbit? And then you go and calculate the orbit. So you keep on, you know, trying different positions, different sizes until you get something that fits the observed data. So he figured out where it should be and how large it would need to be. And he was in contact with a young astronomer named Johann Galle at the Berlin Observatory, who was only an assistant, but they had some correspondence. So anyway, Leverrier writes to Johann Galle, says, you know, why don't you look for this planet, this unknown planet? So they had a 9-inch Fraunhofer refractor there. So Johann Galle, like I said, he was an assistant. He goes to his boss, who was Johann Encke of Encke's Comet. And I said, I got this letter from Leverrier, and he wants me to look for this planet. Encke thought it was a big waste of time. Like, how could you even do that? How could you even predict where a planet would be? You know, he didn't believe it. But he said, look, I'm not using the observatory tonight. He had some big dinner he had to go to. He says, you're allowed to go and, yeah, spend one night with it. See if you can find it. So Galle goes to the observatory, and he takes with him a student, Heinrich d'Arrest. I don't know much about him, but there's a comet named after him. He says, come and help me. So they go and look for this planet. Couldn't really find anything. There's too many stars. What could it be? And then d'Arrest, he says, hey, do you know what? Encke, our boss Encke, he's got this new unpublished, like brand new unpublished atlas of the sky that he's looking at. Let's go and grab it out of his office and use that. So they get this unpublished sheet from the atlas. They go back to the observatory, and with Galle looking at the eyepiece and d'Arrest checking off stars, they go through all the stars that Galle. So they finally found one that's not in the atlas. So they figure they found it, and so they go back and tell Encke, hey, we think we found it. And he said, well, you better look again tomorrow. And so they did, and of course it moved. So they had discovered Neptune. Now there's quite a bit of controversy. There's a whole book on this that's worth reading. It's called The Neptune File by Tom Standage. You should read that. There was a lot of controversy because there was an English astronomer named John Couch Adams that was doing the same work, but he couldn't get his people to believe in him either. And he was trying to get them to look for it, and they wouldn't do it. They wouldn't give him any observatory time. But when they knew he was working on it, but when they announced it from Berlin Observatory and was giving credit to Leverrier, all of a sudden the Brits kind of got like, well, no, we got this guy here. He figured it out. So there was a big controversy, but it ended up being resolved in a nice way. Okay. So Heinrich Schumacher, who was the editor of a German astronomy journal and Leverrier's mentor, he said, this is the noblest triumph of theory that I know. And at that instant, that was like, it was truly the triumph of classical celestial mechanics, because Neptune, it was the last major planet discovered in the solar system, and it's the first one that's position was predicted using celestial mechanics. So that was like a high point of this work. Everything beyond that, like there's really been no advancement on classical celestial mechanics. But there's still remain the problem of Mercury's precession, and the guy who gets credit for figuring that out is Einstein. Now Einstein did a lot of things, and anyway, he came up with a lot of discoveries. He developed the general theory of relativity, and he made a number of predictions of that theory that have all been confirmed to support the theory. This is more than 100 years ago now. So he basically replaced Newton's inverse law of gravity by warping of space and time by the presence of a massive object. Don't have time to go into how that works, but he showed, one of his early papers showed that if you applied this theory of relativity to the orbit of Mercury, it totally explained the precession of the perihelion of Mercury, in addition to the normal perturbations, classical mechanics perturbations. The difference between the observations and the model was exactly what was predicted by general theory of relativity. So, well, we've got that one figured out. No planet Vulcan. In the theory of relativity, no closed elliptical orbits are possible. That's just the way it works out. So coming into the modern era, today astronomers understand the fundamental physics of what makes the worlds go round. And you might wonder, how do you put all of this, how can you simulate this and display it in an app in a phone in your pocket? It's crazy. And the answer might actually surprise people. Your phone isn't solving Kepler's equations or Newton's laws of motion or calculating perturbations or general relativity corrections. What it is doing is using a modern form of epicycles. Okay, and this is how it works. You put all the equations of motion into a computer. So you've got Newtonian gravity mechanics, relativistic corrections, and non-gravitational forces. Each body's starting position is provided based on good measurements. And then you compute the heck out of these equations on a supercomputer using numerical algorithms way into the future and way into the past. So now you have time series of all the positions of the planets. You've got these huge time series that have been computed. The next thing that happens is you fit, kind of like you've heard of, you guys know about Fourier series, right?
Maybe you can refresh us on that one, Dave.
Yeah, I don't know that.
Okay, well, Fourier came up with this idea of representing, especially periodic motion. He basically said you could simulate the motion, any time series, basically, if you had a bunch of sinusoidal oscillations, different amplitudes, frequencies, and phases, and you could, if you had enough of these terms, different frequencies and so on, you could draw any curve. It's called the Fourier series, and there's a whole method for figuring out those components. But you can have a finite sum of these circular motions. Well, this is exactly what epicycles are. I mean, it's exactly the same thing. So what they did, and then Pierre Bretagnon, the Frenchman, who sadly passed, he developed this, it's called the, it's French, I got to look this up here. It's called VSOP, Variation Séculaire des Orbites Planétaires. And he worked in the Bureau of Longitudes of Paris Observatory. He came up with this mathematical model of fitting all of these motions and coming up with these different components. And it is these numbers that are put into your computer, your cell phone, and it's quite straightforward to just do those computations and add them up. They can do it lightning fast. But essentially, we're back to circles upon circles. And I don't know much about this. The guy who knew a lot about it was Dave Lane, and he's no longer with us. But that's where we are today. So in many ways, Bretagnon was the natural successor to Laplace and Leverrier, and by extension, Ptolemy. So in conclusion, this history that I have just given you, it spans a very long period of time, and I've left out a lot of details. So what's happened over the millennia, our view of the cosmos deepened, each thinker building on the knowledge established before. And the theories of planetary motion were continually refined to agree with the continually improved observations. You see, it's kind of a leapfrog thing. The models get better, then the measurements get better, then you have to have better models and so on. So the Greeks were really the first that applied geometry to the problem. And over time, we figured out what the underlying physics was. And so this circle upon circle idea has been revived for the purpose of computing positions. And we can predict their positions as precisely as needed. So anybody can find the positions of the planets, asteroids, what have you, comets, with a device that fits in your pocket. And we've come a really long way, but in some ways, we've come full circle. And that's the end of my story.
Well, it's a nice story, Dave.
Yeah, that was really good. I enjoyed that quite a bit. Planetary motion is something that has always intrigued me. It's one of the neat things to observe, especially when it's moving in real time. And just need to understand how we came to know all of this stuff.
Yeah, yeah.
And Dave, I gotta ask, was Gauss or Gauss, is that of, and you, I feel like you should know this, the answer to this question, even though it's not germane to the central tenet of this conversation, but is Gauss or Gauss the same?
Gauss?
Yeah. Is that the same scientist who came up with the charging of the ships as they go around the world, and then they have to de-Gauss them when
Well, I think what happened there is the System International Unit for the magnetic strength of the magnetic field was named after Gauss.
Oh,
that I know for sure. What, off the top of my head, I'm not aware of any contribution he made to electromagnetic theory, but hush my mouth. I mean, he may have. I only looked. He has a significant role in what happened in the story I just told. A significant role, but I would say a secondary role, because I think anyone could have figured that out. I don't think he's the one that happened to. And the thing is, with all of these things, there's so many people and there's so many ideas. You just can't go down all those avenues and kind of burrow down. Like, I would never have finished.
Yeah.
I was doing a lot of reading, and I found it really, like, even to come up with the story I just told you, it's a lot of reading and compressing and figuring what to leave out. At any point along that storyline, you could jump and go down an avenue and, look at the story of De Rest or Gall, or, I admit I've left out many, many details. Tried to just hit the highlights, right?
Yeah, exactly. I did look it up. 471p comets, periodic comets.
Okay, that many, huh?
That have been named. I should say named and numbered. And then I believe, I just looked it up real quick. The total number of identified individual comets is at 3,992. So 8 more comets, which probably will happen this year. Hopefully, maybe some bright ones. Then we'll be at 4,000.
Yeah. So that shows you that the vast majority of comets just come once and take off again.
Mm-hmm.
Or they might be very, very long period comets, which in effect, are going to take thousands of years to come back, But I feel like the periodic ones are probably comets that come in from way out there, and then by interaction with the planets, some of them just get flung out again. But I think some of them, their orbits get perturbed and they get captured, right?
Mm.
And there's books and books about that as well. But
I noticed you've got Dreyer's A History of Astronomy from Thales to Kepler.
Yes.
That seems like an interesting book.
Yeah, and I don't know. I don't think I put Neptune file on that. I should have. If you guys could get a hold of this book, the Neptune file, this is excellent story of what I compressed it into like 2 paragraphs, but the story of Leverrier and John Couch Adams and the Astronomer Royal and all the different people and now what was going on.
Oh, it's in here. It's second from the last.
Oh, I did have it in there. Great. Yeah.
Stanage.
Yeah. Okay, good. I forgot that I put it in there.
Berkeley Books, New York.
That itself is a fascinating story, and I was just remarking on that the other day that so it's like an assistant at the university and a student were like sneaking into the observatory and grabbing this chart, from the boss's office. They snuck into his office and got it, and they go and discover a planet. I love it.
Very cool. Very cool. Well, yeah, that was fascinating, Dave. And I enjoyed reading the article when you sent it to me back around the New Year's as well. It kind of, it does succinctly distill down the major physics and, planetary dynamics that goes into what happens on your cell phone when you go to look up what Jupiter is tonight, for example. It's pretty cool.
Yeah.
Cool.
Do you think it's prize winning?
Oh, for sure. I'll give you the biggest prize of all, which is appearing on our show.
Well, this is the first time this material has been shared with the public. So you guys should put a feather in your cap.
Oh,
I was told I couldn't publish it elsewhere, but nobody said I couldn't have a podcast. So.
Well, we appreciate that, Dave.
Yeah, awesome. Cool. Well, Shane, do you have anything to add?
No, thanks, Dave. As always, really enjoyed hearing you speak, and it's always well researched and very interesting. So thank you very much.
Well, it was my pleasure to share that with you.
Thanks so much, Dave. And thanks to everybody for listening. Please subscribe and share the show with other stargazers you know. Send us your show ideas, observations, and questions to actualastronomy@gmail.com.
Thank you, everyone, for listening, and we hope you enjoyed the show. If you are interested in more information, would like to contact us, or if you would like to support the podcast, check out our website, actualastronomy.com.